Good morning, everybody. So my name is Mark Russinovich. I'm CTO of Azure. I've been in Azure for over 20 years now, and been working on confidential computing for a little bit of that time as well. And I thought this morning, instead of making this a Microsoft Azure sales pitch, I would actually tell you a little bit about what we're doing and frame it in some of the terminology that we've decided we need to adopt, and we actually are encouraging the industry to adopt to represent what confidential computing is in its various deployment forms. So as far as Microsoft's Azure's history in confidential computing, we've been working on this, like I said, for a while, over 10 years now. In fact, we coined the term confidential computing back in this paper in 2015. And through that time, we've been deploying confidential computing hardware, working closely with our hardware partners, Intel, AMD, NVIDIA. And we've also been offering services on top of that, both the base primitive services like confidential virtual machines and confidential containers, SGX enclaves, as well as higher level services, PaaS services that are built on top of that confidential hardware and those primitives. In the process of doing this, we've identified a core set of primitive services that we consider the root of trust for confidential computing. And the reason that I'm going to talk about this here is kind of lays the framework for the various deployment options that confidential computing offers and the guarantees that you can derive from those different deployment offerings. This root of trust starts, of course, with the TEE. But a TEE with code in it and with attestation and the protection, the encryption that TEE provides to the code and data within it must be available to a relying party to verify. And so a couple of services support that, an attestation service and a key release service. The attestation service provides a token. The token is then presented to the key release service, the key management service, that then releases a key based on policy for that release to the TEE, and therefore it can then decrypt the data and process it in the clear, protected with that encryption. Now, this spectrum of confidential computing guarantees goes from easier adoption all the way to very strong guarantees that you can derive based on the way that the application's architected on top of these core primitives and that core root of trust. I'll start by talking a little bit about the lift and shift. This is what a lot of our customers are doing, and this is what we're doing with some of our services internally in Azure at Microsoft, is moving those services into confidential virtual machines or confidential containers, but primarily confidential virtual machines where the confidential computing gives you protection from the surrounding environment. And then we've got in confidential computing, and this is what we're using to describe when you take an application and actually architect it so that you've got protection of the data through its entire life cycle, not just from the underlying infrastructure. And then finally, transparent confidential computing, which builds on the previous one, but now brings in verified auditability for the code that is able to access the data, what is in what we call the confidential trust boundary. So I'll talk a little bit about an example or examples for each of these at Microsoft, starting with on confidential computing. And this one is derived, this example is derived from an announcement we made about a year and a half ago when we introduced Secure Future Initiative, a program at Microsoft that that echoes Satya's endorsement of security being the #1 priority for the company. And this was in response to various threat actors that had penetrated our infrastructure. In one case, one of the threat actors, Storm 558, a Chinese threat actor, was able to get a signing key for our Microsoft consumer accounts. Their goal was to obtain emails from US government personnel using that access. So as part of this, we promised to protect the token signing keys with confidential computing and with hardware HSMs. And we started a migration into confidential virtual machines. This is a lift and shift migration of our token signing services, both our consumer token signing services as well as our commercial or enterprise token signing services, Entra. And I am proud to announce that you can see here in April, we completed the 100% migration of our consumer signing services into confidential virtual machines and HSMs. And we're making great progress on the migration of Entra. This migration is a massive confidential computing migration, which is why it's taking some time. We're deploying confidential computing hardware into every single of the 70+ regions Azure has worldwide. And we're moving the tens of thousands. And by the time this is done, this will be roughly an order of 100,000 virtual machines running in confidential computing across the world. Now, that is on. That's a lift and shift. But where we want to go is actually to in confidential computing and beyond. Within confidential computing, like I said, you design the application to protect the data in encrypted form with confidential protection through its entire lifecycle. And this requires careful architecture, which is why it takes some time. One of the ways that we're leveraging in confidential computing is to overcome the risk that a public cloud presents to Microsoft's most sensitive data. And believe it or not, we've had most of our services completely migrate to Azure, close to 100% of them across Microsoft. There was a services that we consider are high-value assets that we kept in what we call on-premises environments because the security requirements for them are so high. An example of that is our payment systems. Our payment systems protect the consumer credit cards that we process constantly. We process over 1 billion consumer credit card transactions a year from 300 million different credit cards. This is, of course, a very high-value target for a threat actor. And we had those deployed on-premises with their own networks, their own identity systems, their own hardware, their own cages. Working with that team, the confidential computing team in Azure, we're able to have mitigating controls using confidential computing for all of the different protections they achieved on premises, unlocking a migration to the public cloud. And this is what that architecture effectively looks like, a simplified form of it. But you can see that there's two key microservices involved with encoding those credit cards and tokenizing them, something well known in PCI payment systems, so that they're basically encrypted with keys and HSMs. And so from this perspective, the credit cards, once they enter the system, are protected through their entire life cycle from everything outside. The operators, the infrastructure are kept out and cannot get access to those credit cards. So we've taken every step to effectively create the same protections we had with this isolated on-premises environment in a public cloud. Another example, and this one, we're going to have a blog post literally within the next week, announcing this, the migration of Microsoft licensing services to confidential computing in our public cloud. Again, very high-value asset. This protects the licensing keys for Windows, for Microsoft Store apps, for Xbox games. It processes 70 billion license transactions per month. And so this was another case, its own isolated on-premises environment using confidential computing, was able to provide mitigating controls by putting that licensing service inside of confidential computing. And that architecture is a little bit different. We're having a little bit different journey for every one of them, every one of these services. As we learn how to deploy and architect confidential computing, this one is using a microservices cluster, and you can see this is running inside of confidential virtual machines with microservices running inside of them. We also, just like Google, also are moving towards privacy-protected confidential ad serving. And so this is to mitigate the risk of cookies and tracking of user behaviors across different devices by completely protecting their privacy inside of confidential computing enclave so that the advertisers cannot do correlations across different user requests. And even the platform, we cannot see what the consumers are doing. It's purely a blind auction offering the ads to the users based off interest groups that are protected with confidential computing inside of trusted execution environments, as you can see here. We also, and I talked about this last year, in fact, I showed a demonstration of this, confidential RAG running on confidential GPUs from NVIDIA. which are now in production in Azure. And last fall, we had launched a public preview of confidential inferencing with Azure OpenAI's Whisper model. And this came from me talking to various customers that were specifically in the finance sector that have to transcribe speech and audit it for fraud. That's very sensitive speech because that can be market-moving information contained in those conversations. And most of those customers were doing that kind of transcription on-premises or had very complex architectures that leverage cloud and on-premises. And when I would talk to them about confidential computing, they would say, what about confidential Whisper? That would allow us to leverage cloud PaaS managed services rather than have to do this ourselves on-premises. So we launched this service last year, which relies on an AI application, an oblivious HTTP proxy that an enterprise can deploy to completely anonymize the IP addresses going into the public cloud service so that they can't even be traced to particular customers. That hits a front end, with the encrypted prompts. That front end also implements oblivious HTTP gateway proxy functionality that finally gets back into the confidential virtual machines that are connected to confidential GPUs, perform the inference, and then send back an encrypted response. So the consumers, the transcription, the speech and the transcribed speech, protected end-to-end with complete anonymity from Microsoft, from Azure, from the Azure OpenAI operators and developers. Now, that gives us a certain level of protection. But where we really want to go is transparent confidential computing. Because with transparent confidential computing, you protect the code and data throughout its entire lifecycle with confidential computing. But you can also prove what had access to the data at any point in time. And this is we call code transparency. Because when we take a look at what customers really want, they want protection from the cloud. They want protection from malicious software that has access to their data. And if they really want full control, what they do is leverage effectively infrastructure as a service, where they take their code, they put it in a confidential TEE, they put their data in there, they do a key release dance using their own attestation verifications, and now they believe that they've got full control over what has access to their data. But infrastructure as a service is extremely limiting. You can't leverage cloud services. And if you're importing libraries from somebody or using somebody else's code at all, then you're letting them into your confidential trust boundary. And you either have a choice then. Do you just implicitly trust them? Or do you require verified trust? The ability to have guaranteed ability to audit exactly what code they had deployed at any point in time. Because auditing up front is actually not practical. And this is one of the things that we wrestle with is, hey, customers are going to want to review the code. But reviewing tens of thousands, hundreds of thousands, or millions of lines of code changes is just impractical. There's IP issues as well with that. And anybody familiar with Ken Thompson's reflections on trusting trust knows that even auditing the code, if you don't know what you're looking for, you might not be able to find any sign of misbehavior. But if you suspect there's misbehavior or have evidence of misbehavior, having the guaranteed ability to go find where that misbehavior was located and then hold the party accountable is a very powerful disincentive for somebody misbehaving. And so that's where we're going, is being able to provide guaranteed auditing for whatever had access to the data. So we published a paper in ACMQ, you can see about 1.5 years ago, Why Should I Trust Your Code, that talks exactly about how we plan on doing this. And we've started on that journey. We've created something internally called Code Transparency Service. That actually is going to be announced as a public preview shortly as Cloud Transparency Service. And the idea here is that it signs, basically, it signs statements and records those statements in a ledger and provides receipts back to whoever's transparency. And one of the ways that we're integrating this is into build pipelines for confidential attested builds. Because if you're building in a confidential build pipeline, you've got measurements of exactly what goes into the build and what came out of the build. And once you have those measurements, and you've got those assets that went into the build process, the tools and the source code, escrowed, and you have that signed, put in a ledger that's immutable, which again is built on top of confidential computing technology using the confidential consortium framework that we developed and that open sourced, that you can enforce policies for what gets signed to make sure it has to be confidential and transparent. And those confidential services then can leverage those receipts to even automated upgrade themselves, enforcing a policy that the code that they're upgrading to has to be transparent and has to meet those policies potentially of being audited or escrowed under a third party's control, which guarantees the relying parties the ability to go and audit exactly what went into their confidential trust boundary. And we're building on top of this something internally called Project X-Ray, because what we want to do is also leverage that CTS service to sign SBOMs coming out of our build pipelines as well, so that customers can know, we can know internally, when we have an SBOM, it is cryptographically connected to code that was built in a confidential build pipeline. And so this is what we're calling Project X-Ray. It adheres to the SCIT standard from IETF for the schema that goes into that ledger. Those SBOMs are signed, they're stored in Microsoft Artifact Registry, MAR, and then can be queried through the Azure Resource Graph. So this is a system that's under development right now. And this is the future of software production inside of Microsoft. Confidential build pipelines, CTS, SBOMs, artifacts stored inside of Microsoft Artifact Registry, and then queryable for at-scale analytics inside of the Azure Resource Graph. And then one final example of transparent confidential computing that I'm very excited about is this idea that we came up with to address a scenario that I live through just about every day, and I'm sure many of you do as well. And let me illustrate that scenario, which is you having to give somebody a lot of personal information that is completely irrelevant to what you're trying to do. You're basically leaking information every day, all the time. Here's an example. Bob's got a boat. He's got a policy around who can rent that boat. And when Alice comes along, the way that Bob today would verify that Alice meets that policy is asking for a lot of personal identifiable information, like a photo ID. Let me see your driver's license, or let me see another government-issued ID. At that point, they don't just have that Alice is 21 years old. They've got exactly where she lives. They've got a lot of information about her description. They've even got her picture. How many of you had somebody photocopy your driver's license recently? Quite a few of you. So this is just huge violation of our privacy, is leaking all this information. Now, zero-knowledge proofs is one of the ways that people believe this can be addressed. Zero-knowledge proofs are a way to prove something without revealing any information other than what's required for the proof, and it's mathematically cryptographic proofs. But the challenge with zero-knowledge proofs is that they're computationally extremely expensive. They're also very complicated in terms of architecture, which goes with the performance. If you architected it incorrectly, your performance will just be impractical. But even in the most optimized zero-knowledge proofs, they can be very expensive to produce, and at the same time, they're very rigid. Now, in the case of something like having a government-issued ID that has a whole bunch of personally identifiable information, you'd rather not produce all of the information. You'd rather be selective about what information you want to provide to match somebody's policy. Because one relying party might say you need to be over 21, another one might say you need to be 21 and be a resident of a particular state or a particular city. So you want to reveal specific pieces of information. And with zero-knowledge proofs, you've got to know a priori exactly all the combinations that you want to make available. So we've come up with an idea that we call confidential computing proofs. And it's pretty straightforward. Once you have transparency, you can design a proofing system that's very general and based on confidential computing, selectively disclose information from, for example, these signed identifications, these signed documents inside of a wallet that's in a TEE that then would say, oh, you want to verify that I'm over 21 and a resident of this particular state? Well, I've got a document that has that information by a party that you trust, according to your policy, the state of Washington, for example. And so I'm going to provide you proof based on confidential computing, which shows you the transparency of the code that implements that proof that you trust, and the fact that that code verified these aspects of those documents. And given that I trust the wallet and the TEE, given that I have a policy that says documents have to be signed by certain parties, that I then trust the state of Washington to attest to my age and my state of residency, then I can go ahead and verify that. So we believe that this is the key to practical privacy-preserving interactions in the real world at scale that goes beyond what cryptographic techniques can achieve. And the fact that we're already relying on wallets for much of our privacy and confidentiality already today, this is another step leveraging confidential computing kind of in a different way and more general a way. So this is something that we're also working on. So that's, I think, a great example of transparent confidential computing. So that brings me to the conclusion. And I think what I wanted to do this morning was to share with you this spectrum, because one of the challenges that I run into at Microsoft is when we say confidential computing, people are unsure what exactly we mean. It can mean in, on, or transparent. And each of those have different guarantees, and each of those require different types of architectural work to achieve. So this is, I think, terminology that might be helpful for everybody to adopt, so that we know that confidential computing isn't just one size fits all, and it's actually a spectrum where on the far right is where we all want to head. So with that, I want to thank you very much. It's been an honor here speaking again at the Confidential Computing Summit.